Okay, in this video we're going to take a look at using ProEngineer to calculate stress concentration from figure A15-1 of the Shigley textbook for our class. And this would be stress concentration for a flat plate with a hole drilled in the center of the flat plate and a uniform tension load being applied. And because of the overall geometry and loading of this thing and the nature of it, we're going to be able to use several simplifications. First of all, we're going to be able to use, because of the double symmetry, we're going to be able to use a quarter model, a 1/4 model of this thing. And also, because everything about this is planar, we're going to be able to treat this as a plane stress model. So we'll look at all the details for that. So let's move the picture out of the way and get started. So first thing we'll do is go into the sketcher and I'll sketch on the front plane. I got that one, and middle click and accept all the other defaults. And first thing I'm going to do is create an arc that is centered at the origin, starting there, ending there, and then I'm going to create a series of straight lines to finish up the geometry, and then I will go and dimension the geometry and get the details right. Middle click to end that. Selecting things, I'm going to do a Control A to select everything. No, I guess that doesn't select everything. Do you want to quit? No, I don't want to quit. So I'll just drag and select everything. And then I'll go to my geometry modifier tool right here, and I will say lock the scale. And I will be changing my 103 dimension to 0.5. Didn't type that well. 0.5. Enter. And when I accept that, it should rescale everything and get it down into an acceptable size. I'm going to change this to a 3 inches, and I'm going to redimension this back end. Middle click, and I'm going to make that dimension a 1, and this one is already a 0.5. So there's my sketch. I will exit the sketch. I will click here to create the solid, and that solid I will make 0.5 thick. Okay, and so there's my geometry. I will accept the geometry, and now before I go any further, I know that I'm going to, no, I guess I'll go ahead and show the mistake. Let's go Applications, Mechanica. I look at my units and I see that I'm going to be forced to enter forces in units of inch pound mass per second squared. Sure don't want to do that, so I'm going to cancel. Go to Edit, Setup, Units, and I want inch pound seconds as my unit system, and I'm going to set that. We've already talked in class about the difference between convert and interpret, and in this case it just doesn't matter. And so I will now close that and say done. And now when I go into Applications, Mechanica, it says I'll be entering forces in pounds force, and that's much more tenable. So we will continue. Because this is the first time I'm going into Mechanica with this particular model, I can go to Advanced and select 2D plane stress. I'm not going to. I'm going to make the mistake of going into it in 3D. Okay, and if I look down here, it says Structure 3D, and oops, that's not what I want, so let's go change that by going Edit, Mechanica Model Setup, and I'm right back to this dialog, Advanced, 2D Plane Stress, or a thin plate. Cartesian coordinate system I will select will be the world coordinate system. Okay, and I will then say select geometrical reference. I need to select the surface that is in the XY plane of that coordinate system. So there's my surface. Okay. So I'm going to lose all simulation modeling that I've done. I will confirm that because that's what I expected. And now I am in Mechanica, and I do have my geometry in the XY plane, and now I'm ready to do all the things necessary to create an FEA model And first thing I'll do is apply some constraints to the model, and I'll do a displacement constraint. Now, because I'm working on my model as just a surface or a face, then my constraints will be edges. And so I'm going to select this bottom edge using a symmetry constraint and say that it can't move in the Y, but it's free to move in the X. Okay, that one's done. I will select this, I'll pre-select this edge if I want to, and then go into constraint, and I'll say that that edge can't move in the X direction, but it's free to move in the Y direction. Okay, that has fully locked my model down. Because it is a 2D model, it can't move in the Z direction. There's no consideration of the Z direction. So my model is fully constrained in the X and Y, and so now I need to apply some loading to the part. And let's see, and I will also go ahead and apply, well, I could apply a rigid constraint to this. Maybe I do, maybe I don't. We may play with that. So right now, where's my rigid constraint? Rigid link. I'm going to apply a rigid link constraint to this edge and say OK. And then I'm going to apply a load to that edge. And I am going to use edge. I'll apply a load to that edge in the positive X direction of 100 pounds. I'll preview it. That looks very good. Okay. Now, I've got geometry. I've got constraints. I've got loads. What I don't yet have is materials, and I haven't specified a thickness. And what I have to do for a plane stress model is go to the shell element tool. I'll click on shell, and I'm going to click on that surface, and we'll put in a thickness of any number that I like. Let's go ahead and put in a thickness of 0.5. Primary thing that does is give my forces meaning now. And let's see, I don't have any materials in the part, so I'm going to click on more, and I will add steel to the model. Okay, and now my part is made of steel. Okay, and this thing should be ready to run. So I'll go up here to the boxes that are stacked, File, New Static, and let me call this one ShigleyA15-1, A15-1. And for the first run, we will go ahead and with the single pass adaptive, and we'll just find out if it works. Illegal characters in the name. Looks like it doesn't like the dash, I suspect. So we'll call this A15. Let's try _1. Let's see if it likes that any better. Okay, it's happy with that. I'm going to run it. Yes. And we'll view the results. Pass 1. Let's close it. Let's see, did it complete successfully or unsuccessfully? There's pass 2. Okay, I've got a phone call coming in. I'm going to pause. Okay, well, I answered the phone call and I am back, and so this thing did run. We'll go ahead and close it. Well, let's go ahead and look at the maximum von Mises stress. It says 799. Let's close that. We'll take a quick look at the results. Okay, and show. We do see sort of a stress concentration behavior. We'll make a change and show the elements, and probably only 2 elements. Okay, and show. Yes, and this is a 2-element model, which isn't very good. And it was a single pass anyway, so for 2 reasons, not very good. So let's go into AutoGem and Control, and on this individual, not surface, let's go with edges and curves on this edge and this edge. I'll control the element size to be about a 0.1 should be interesting enough. 0.1. Okay. And let's go back to now analysis. And let's go ahead and change this into a multipass adaptive. And let's aim for a 1%, which is not going to be reached. And maximum polynomial order. This is going to run fast. So yes, no. Let's watch it run. 3, 5, past 7. It's done. Did it converge or not? The analysis did converge to within 1%. Let's take a look at the results. And let's go ahead and display the element edges. Okay, and show. So we have more edges along here. And our maximum stress of 868. Let's go with info, model max. It shows a little bit hard to see, but that is 868 right there in that corner. Let's view the front of this thing. Okay, now let's do a quick calculation of the stress concentration. And so our load was 100 pounds. It'll be acting on this face, which is a 0.5 by 0.5. So force of 100 divided by an area of 0.5 divided by 0.5 equals a 400 psi nominal stress on this surface. We will divide by 869 equals, and take the reciprocal of that, and we get about a 2.17, and that is absolutely in the ballpark as compared to the chart having a D over W on this scale. Let's go ahead and zoom in quite a bit on this one so it'll show up decent on the movie. Okay. Well, I'm having a little trouble getting that to scale and scroll nicely, but here we go. Okay, D over W, where our diameter of the hole was 1, and for the whole model this was 2. So that'd be a 0.5 D over W. And I'm sorry, I'm looking at the wrong plot still. Right geometry, wrong plot. Okay, D over W of 0.5 would bring us right here. Our scale axes, let's go ahead and bring that into view. This is 2, this is 2.2, so the middle would be 2.5, 2.1. I want to be on this 0.5 line, 2.1. 2.15 would be around right around here, so I would have to call that somewhere in the neighborhood of 2.18 or something like that. And we calculated a value of 2.172. That's certainly in the ballpark. We'll move the calculator out of the way. We'll move this out of the way. While we're here, we'll go ahead and edit the view, and let's see what the deformed shape looks like. Okay, and show, and that seems very reasonable. Seems like the way that I would expect it to behave roughly. An interesting question might be, what else could we calculate, maybe by hand, just to see if this thing is giving reasonable answers? And so if we wanted to, we could explore the model a bit more and say, maybe calculate this deflection and just make sure we're getting some kind of a nominal gross behavior. So let's take a look at, rather than stresses, let's look at displacement. And let's look at displacement in the x direction. Okay, we'll do an OK and show. We see a maximum displacement in the x direction of 2.66 times 10 to the minus fifth inches. Let's just browse this a little bit with the dynamic query. Okay, 2.58, 2.40. Let's look at, let's close this and let's look at the Model Max. Info Model Max is this lower corner, it would appear, of the 2.66. We're roughly in the 2.6, 2.5 times 10 to the minus fifth. If we were going to calculate this deflection and assume that the entire thing was a complete rectangle, we would use an FL cubed over 3EI. The F would be 100 pounds, L would be 3 inches, E is 29 million. If you look up the material properties, and maybe we should do that in a moment, the L is 29 million. The E is 29 million. The I would be, no, that's FL over AE. Sorry, I was thinking the wrong thing. FL over AE, so that's going to be quite easy. And we're talking about the area of the nominal cross-section. So the force, 100, times the length, 3 inches, divided by 29,000,000. That's FL over E. And then when to divide by the area, we need to divide by a 1 and a 0.5 thickness. So divide by 0.5. We won't bother dividing by the 1. And we get a deflection of 2.07. This has deflected times 10 to the minus fifth. This has deflected a bit more than that. Why a bit more than that? Well, one answer is we have changed the material or changed the geometry significantly, so we would expect it to deform more because of the hole. But at least we are in the ballpark, and that's probably a reasonable check. If we really wanted to check our model, what we might do is just get rid of the hole and make sure we could match FL over AE kind of deflections for a model that didn't even have a hole. Okay, I think we'll just clear ourselves in the reasonable area now. What we could do if we wanted to is play with other things like refining this mesh even further. And so we got, let's go back to viewing stresses, or view stress, it picked von Mises, OK and show. Okay, let's remember that 868, and let's go refine the mesh a little differently, and then run it again. So that was an 868. No, I won't save that. We will go to AutoGem, right-click, edit definition, and let's try a 0.05. Okay. We will bring up the analysis. We will run it with a yes and a no, and we'll watch it happen over here in this right-hand screen. It should take a little bit longer. Okay, did it converge? It did converge, and so we can go look at the results. Okay, and show 870 instead of an 868. I'd say we are definitely within an acceptable precision or an acceptable accuracy, and so we could stop it right here. About the only other thing we could play with is since it converged, we could allow it to go to a higher order by reducing the error term in the analysis box. I think I'll stop this one right here, and you've seen a plane stress element being run to calculate the stress concentration of a hole in a flat plate loaded under axial tension.